Brilliant. Awesome. Well, I'll try not to touch the computer again and cause some technical defaults. So thanks for the introduction. My name's Robertson. I'm from the University of Sydney in Australia. And today I'm going to talk to you about organ transplantation, how we're building some transferable models to kind of look at pan-organ allograft dysfunction rather than the organ-specific paradigms that's kind of common in the transplant world. Okay, so as an introduction to organ transplantation, I'm sure we've kind of all heard of it, but organ transplantation remains the only solution for end-stage organ failure in patients that have a range of different kind of phenotypes of dysfunction across their organs. And so heart, lung, liver, and kidney transplantation is kind of a common practice across the world, particularly in Australia, where we do kind of national transplantations rather than having like a state-based program like in the US. And so often when we have these dysfunctions in organ transplantation, whether it be rejection or fibrosis, we almost refer to it as like a man-made illness, whereby we've given our patients organ transplant, and because of their own active immune system, it decides to kind of attempt to kill off this foreign body in a process that's quite natural. And so in a direct context to some of the other diseases that we've heard about today, organ transplantation kind of remains that man-made illness. And so what organ rejection looks like is whereby your own immune system will attack the organ, whether that be in an antibody or kind of innate immune process, resulting in a failed organ. And so currently, like I alluded to at the start, allograft dysfunction or organ transplant dysfunction is kind of kept into its own organ-specific paradigms, whereby your nephrologist or your kidney doctor would go and treat your kidney transplant, your lung physician would treat your lung transplant. However, the kind of aim of this study was to look at whether or not this man-made illness that our patients are having is common across organs and isn't an organ-specific process. And so in an analogous way to these pan-cancer studies, whereby we look at cancers from a range of different sites and come up with these global conclusions, we wanted to do the same for organ transplantation. And so unlike the field of oncology, whereby there's like the TCGA atlas, where you can kind of go and pull data, unfortunately, lonely organ transplantation doesn't have an atlas that we can go and query. So the first step of our kind of research was to go and set up this atlas to try and look at allograft dysfunction across our different organs. So I thought I'd just briefly take you through it, but obviously with time constraints today, I won't be able to go through all the analysis that we've done. But ProMAD, or the Pan-Organ Resource for Molecular Allograft Dysfunction, samples a variety of different sources, so whole blood, PBMCs, and allograft biopsies. We take from 4 different organs, mainly kidney, heart, liver, and lung. Like I said, we do kind of cover a range of different outcomes for our organ transplantation patients. In this talk, however, I'll only be talking about allograft rejection. I thought that it was just a good point to emphasize the scale at which we're talking about in this data collection process, whereby we went and found 233 publicly available data sets that contained over 15,000 different transcriptomic samples. And so just to, again, kind of be clear, these were transcriptomes. So we're talking about microarray, RNA-seq, nanostring. And so again, I won't be able to kind of cover all the analysis that we've done with this atlas, but I thought I'd just cover a very specific kind of problem in the field of organ transplantation, and that's predicting rejection from a peripheral blood sample. And so you can imagine that if you've just had a transplant whereby there's a new organ that's now saving your life, a doctor coming with a biopsy needle to go and take chunks of that organ is probably not an ideal situation. And so predicting rejection or allograft dysfunction based on a peripheral blood sample is ideal. And so what we did is, in our atlas, we took the 28 data sets containing over 2,400 whole blood samples from our patients to try and come up with a classifier that's able to detect rejection from these peripheral blood samples. So as you can see here, the data sets that we included were kind of heavily preference towards kidney transplantation. And so that's something that we had to go and design models that kind of took that into account, whereby we're not just having a kidney-specific model, but having a pan-organ model. And so one of the first things that we thought about was whether or not we can just go and use a standard batch correction algorithm to kind of just pool all our samples into one kind of large model. And so batch correction can often, if you've played with it, feel more like an art, whereby you're trying to remove all the technical variation that's in your across your data sets while maintaining this biological variation. So we didn't think that was a viable option, given that we're now crossing organs. And so potentially now that your batch is confounded with organ, batch correction wasn't an ideal choice. And so several efforts in our lab have kind of looked at whether or not we can build models that are kind of across data sets without the need for batch correction. And briefly, a model that came out last year called CPOP used the principle of ratios. And so if I just plot the normalized expression of 7 data sets here, and I take the ratio of all of our features, what you can see is that ratios start to self-normalize across data sets. And so where before you couldn't build a model across these data sets where you had this variation, when you're taking the ratios, that seems to be a little bit easier. So what we're presenting is called our Transferable Omics Prediction Model, or TOP. And so TOP is an extension of CPOP, which came before, which worked on that ratios idea to build models across these data sets that we've assembled. So briefly, how TOP works is we start with a list of kind of all the data sets that you'd like to integrate. In the same way as previously described, we go and calculate the pairwise ratios of all of our features to kind of get around this normalization problem. Each feature, or for each now ratio within the data sets, we go and calculate a fold change between your 2 conditions. And so in our case, it was our patients with rejection versus those that had an otherwise stably functioning graft. You go and repeat this for all the ratios across all the data sets that you've assembled. So what you're then able to do is go and calculate some summary statistics, mainly the mean of how much these, or the mean fold change of these ratios across your different organs, as well as a standard deviation of how much these ratios are changing, or the fold change of these ratios are changing across your organs. What you're then able to do is go and come up with kind of a test statistic, or kind of like a pseudo test statistic for each ratio, where you're dividing the mean of the fold change in these ratios over the standard deviation. And so if that's all a bit unclear, all you're preferencing is you're trying to make sure that the ratios you're picking up have a large fold change between your conditions, but they have a small standard deviation. So they're changing quite a lot, but they're quite stable across your organs. You do this for all your ratios, and that just gets handed off into a lasso regression, particularly just because when, as I'll show you later, we're interested in having sparse features throughout our model. And so if that kind of all was a bit much, the TOP can be summarized into 3 steps, whereby you highlight your cross-organ ratios, you weight your organs equally, and you go and deploy your lasso regression model. So in kind of experimenting with our model, what we wanted to do was see what happens when I start to sequentially add data sets to kind of get an assessment for the scalability of our model. So if we just go and pick a kind of an independent testing data set, which is one of our in-house data sets, we can sequentially add these training data sets and keep predicting on the same testing data set to assess its scalability. This is what we saw. And so when we start to sequentially add data sets, you can see that our ability to predict on this independent testing set gets quite good, and eventually starts to plateau off as you start to add more data sets. So that was really interesting. We're particularly interested as to why at the start it starts to have these big jumps. So what we wanted to go and assess is kind of where is this increase in model performance coming from? And so I'm sure a lot of us have heard of an R-squared value, whereby I'm measuring the correlation between 2 vectors. Something I hadn't heard of before I started this study was a canonical correlation analysis, or a CCA, which can almost be thought of as an R-squared value, but you're measuring the correlation between 2 data sets. And so in a similar way to this like R-squared value, if you've got a high CCA value, then obviously your data sets are quite correlated. And then if it's not correlated, you don't have a high CCA. Next. And so this is what we saw. So to briefly explain this plot, each point is a pair of data sets that have been used in our TOP model to go and predict on that independent data set I spoke about earlier. So what we're trying to assess here is if I go and calculate the correlation between these two data sets, or our CCA, versus our final prediction on that independent data set. So hopefully what's quite clear is that as you increase the similarity of your two data sets, your performance on that final independent set gets smaller. And as you have data sets that are quite specific or separate or not similar, your ability to predict on that third data set gets a bit better. So this is just highlighting that if you have these dissimilar data sets, your model kind of becomes a bit more robust to the variation that it's going to encounter in the testing phase. And so when we're kind of left with the question of what makes a good top model, adding more data sets and having dissimilar data sets seem to work quite well. Now addressing the question that I posed at the start, can we come up with a model that has this pan-organ feature where we're not having organ-specific models? What we wanted to do was set up a test whereby we create a organ-specific model here at the top, and this is just an example of predicting rejection from heart transplant versus a pan-organ model. So we give these to our top algorithm. Again, like I said, we have an organ-specific and pan-organ model, which finally then gets to test on an independent data set that corresponds to the original organ. Given that we have these public data sets and the sample sizes or the classes are quite imbalanced, we just used AUC as an evaluation metric. So this is what we found. And so this is a slide that's quite impactful. And so what you can see is that here in yellow is the same model, or our pan-organ model, that's trained across all of our organs, wherein the individual colors are your organ-specific models. And so if you just focus on heart transplant here, we can see that adding information from kidney and liver transplants actually helps your prediction of heart transplant outcomes. So I should have explained that each point is a prediction on an independent testing set, and these lines join the same testing set. And so what we wanted to do is go and, like I said, top is introduces sparsity into the features that you have given you're applying a lasso regression. So we wanted to see how many features do you need in order to make these classifiers work quite well. So by just kind of taking the lambda path of these features in our lasso, we can start to look at how many ratios do you need to make a good prediction. So you can see that 50 ratios is pretty good, but we might be able to get away with 5. And so in the last 5 minutes, minute and a half, not 5, I'm just going to quickly run through our independent cohort that we established to go and assess these pan-organ models. And I'm going to run through it. So AUSCAD is an Australian cohort study out of Westmead. In our Australian cohort study, we're prospectively recruiting patients in our kidney transplant centre to see whether this 5 ratio test is doing quite well. So our patients have a kidney transplant, and 3 months later, they get a blood draw, which is then undergoes RNA sequencing to detect whether or not these patients are currently having a rejection event or otherwise stably functioning. In our cohort, we had 134 patients, with 34 of those having a rejection phenotype at 3 months. And so what we can see is that what we can see on our clinical data, whereby we use 4 conventional biomarkers in kidney transplant, creatinine, proteinuria, EGFR, in the presence of a DSA, is that clinical data doesn't actually help you identify whether or not these patients are having a rejection episode at 3 months post-transplantation. If you use a kidney-specific model, again, just off that 5 ratios, but a kidney-specific model, you do quite a bit better than your clinical data alone. But it's not until you go and look at a pan-organ model that things start to get better. And so while I'll skip over this in the interest of time, we went and explored who we got wrong in our kind of at 3 months post-transplantation. And so in our study setup, we took biopsies of these patients. At the same time, we took blood and did RNA sequencing of the biopsies as well. And it seems as though these patients here that we got wrong compared with this otherwise truly stably functioning patients had phenotypes that were associated with quite high levels of immune activation, at least on a biopsy. And so this is a prospective cohort study, and so it's still not clear how these patients are going to go. But with that, I'll finish and say that we presented ProMAD, which is the first kind of atlas of organ transplant data. We established TOP, which is our framework for building these models across different organs. Using ProMAD, we go and establish a pan-organ blood test for allograft rejection. And given our prospective cohort study, we think that it's doing quite well at the moment. And so with that, I'll thank supervisors, particularly Dr. Ellis Patrick and Professor Jean Yang, for all their guidance over the year that's been this study. Thanks.
Fantastic talk. I think that's very interesting. I actually would like to start with a question. Do you think these approaches can predict rejection before even transplant?
Yeah, so that's an excellent question. So in the data sets that we've curated, we've got 4 data sets that go and examine that question is before the transplant even happens, can we just see who's going to be susceptible to rejection? Early results say that you can, to an extent. I think you get an AUC of 0.65, so it's not great, but it seems as though there's some signal there.
Great.
Cool.
Thanks, very nice talk. So it's really interesting. You're trying to develop a pan tissue signature, I see there's a lot of value to it. But do you think once we accumulate more data sets, do you think it will turn out that we have to actually have a tissue-specific signature?
Yeah, look, I think only time will tell. At least in the context of, I'm not even going to attempt to go back through the slides, but in our kidney-specific one, whereby we did have quite a lot of data, even introducing those few data sets that were left in the heart and the liver. So there was 22 kidney ones, and then there was 5 everything else. So adding those 5 gave you a pretty good performance boost. And so potentially the answers hinting towards a pan-organ one might just be that little bit better. Particularly, and again, the secret sauce might not be in the genes itself, but it might be in just capturing variation, whereby a heart immune response might just look a little bit different to a kidney rejection immune response.
That was a very good talk. Thank you. I have a question. It's more, I guess, on the technical side. You alluded to the fact that if you have the data sets being quite different from each other, you perform better. Do you think there is value in not, I guess, enforcing that your data somewhere are far enough before you analyze them, or introducing some sort of random noise to the data to make them as different as possible? Yeah,
look, and I think that's kind of what our at least preliminary results are showing, is that if you do have data that might be that kind of dissimilar, that variation allows you to kind of capture what goes on in the testing phase. I don't know about adding noise. We haven't really tried that, but definitely kind of capturing that variation, at least at this scale, seems to work pretty well.